Hello Internet friends. In this video we're going to be re-implementing Swift's new observation framework. Observation from scratch, essentially. And in order to do this, we're going to take a few steps. The first step would be to look at the high-level use case, sort of how it was motivated or pitched at WWDC 2023. So I have a file over here, we're going to look at that. But that's fairly high level, so then we're going to see how it actually behaves. We're going to investigate the actual API it exposes and see how it works, not how it's used under the hood by SwiftUI. We can't exactly know that, but we can see what levers it exposes to us. And then finally, we will re-implement it. This will also be in stages. We'll start as simply as possible with just kind of something that works, building just a pedagogical replica that helps us understand how it works, even if it's not as efficient or if it meets every edge case. Then we'll try to identify those and make it closer and closer to the actual implementation, which is actually possible because this code is open sourced in Apple's Swift standard library. We'll talk about that more in this section. But first, let's see what this thing actually is. Maybe you haven't heard of observation yet. So here I have a little example. Here's some SwiftUI code. It's not much code. And here's the rendered view. Essentially, we have some mutable object state here, this suspect who has a name and a suspiciousness quotient. And using this view, you can increase or decrease the suspiciousness, and you'll get a little report below. And this is using APIs that have been around for a few years now. The Observable Object API, this published property wrapper. So nothing here is new just yet. But observation was introduced as a solution to some problems with this API, some performance issues mainly, and some usability problems. First, let's take a look at what we have. So when you were using the old observable object protocol, you needed to have a class that extended observable object, and then you could mark certain properties as published. Then you would have to name the variable that instantiated and held onto that reference to that observable object as a state object. And then if you pass this state object along to some nested view, this suspect view, you would have to mark that with observed objects. So already there are a lot of different property wrappers you have to remember to add, and you have to remember to extend this protocol. It can get a little complicated. So that's just some usability pain, some boilerplate you need. And then there's the performance aspect of it. So let's see what we have here. We have this home view, our root view, that's storing this mutable suspect data, instantiating it and storing it in a state object. And then in the body, we have this little stepper up top that allows us to modify the suspect's suspiciousness using a binding exposed by @published. That's convenient. And then we pass that suspect along to the suspect view, which stores it in this observed object. And this renders basically this form part here. So we print out the name, their suspiciousness as a number, and then some text below. So that's the setup here. What is the issue with this besides the boilerplate? If I open up the debug console here, we can add some prints to our views. So I'm going to go into the body of home view and say print homeview.body. And then I'm going to do the same thing down here in the suspect view and say suspectview.body. And it's re-rendering here. Let me clear out the logs, and we'll see that homeview.body and suspectview.body are both rendered upon first render. That makes sense. In order to generate this UI, we need to call both bodies, see what everything's about. And then when I click plus or minus on suspiciousness here, we'll see that both views are evaluated again. Their body properties are re-evaluated. Actually, let me change this just a little bit to make this instead of a stepper, I'll make it into a button. So I'll say suspect.suspiciousness equals 10. And then I'll have barely suspicious, reset it down to 0. And if I reset and we look here, every time I change the suspiciousness, both views are rendered. But if we think about it, this isn't necessary, really. This home view, in fact, never reads any properties off of suspect. We merely set properties on the suspect. So we don't actually care to re-render ourselves when the suspect's properties changes. It's not going to affect the way this view is laid out at all. We've already passed a reference along to our child. Our child is holding a reference to suspect. It happens to use its properties, so this suspect view would need to re-render, but the home view shouldn't have to. Another issue with this is, let's say this child view did not actually use any of the properties. Let's just say it was this blank view that just said report. Let me remove everything from this. So it's a fairly boring view that, while it holds on to a suspect, doesn't actually ever use it. And if I regenerate this and start mutating the suspect, will see its view is still rendered over and over again. And this is a huge problem with the observable object model, especially the recommendation with SwiftUI, the recommendations that Apple sort of proposes at WWDC, is to use this as your primary method of sharing state across your application. You would have an observable object and you would either pass it along like this, or via an environment object property, passing it along through the environment. Either way, any view that's holding onto an observable object will re-render its body every time that changes, whether or not it cares about any of these properties. Huge performance issue if you have a giant application and every view in your application is holding on to some state object. Every time you change it anywhere, your entire app has to re-render, which can be very expensive, and it causes you to have to break apart your state in interesting ways and really think about this a lot. And ideally, you wouldn't have to think about it so much. Ideally, just using it out of the box would have good performance. So this is why observation came along. So let's migrate over to that very quickly to see how it helps us. Remembering that the goal would be for not every single view to re-render when any property changes. Views should ideally only re-render if properties relevant to them change, which I think makes sense as a goal. Okay, so the first thing we need to do is import observation. It's in a new package there. And then we're going to delete some things. We're going to delete observable object. We're going to delete these published property wrappers. We're going to delete state object, replacing it with state at the top level here. And we're going to delete observed object down here. And next, we're going to use the observable macro. So we're going to add just one macro annotation up here. And with that, let's see if anything has changed. I'm going to open the console, clear everything out. I'm going to restart the preview so we see both views are rendered, both bodies are evaluated at first. And now, if I make changes, nothing is happening, which is interesting. Is it broken? Well, let's remember that I've removed everything from here. So let me undo that, bring this back in, clear it out once more, bring this method back in, re-render. Okay. Both bodies have evaluated. And now when I click on these buttons, we'll see that only the suspect view is re-rendering, which is exactly what we want. Further, if I were to comment out the code that references the suspiciousness, which is the property we're changing here, and only render their name, and then I re-render, when I click on these buttons, we don't see any re-rendering, just this sort of incremental re-rendering that Xcode is doing. And if I were to go up to home view and add a read of the suspect's suspiciousness value here, well then the home view's body is going to change every time because it's reading it, but never the child. So this is pretty cool. We have very granular observation. You create this state, this view state, and you don't re-render your entire application anytime anything changes. The re-renderings are going to be extremely surgical, which is great for everybody. And there's less code, and we just get to delete the concepts of state object and environment object and observed object, all that stuff, which is really wacky. And it is our goal, the rest of the video, is to figure out how this works. And now we're going to see what low-level APIs it exposes to us. So if we want to use observation directly outside of SwiftUI, how does it work? How does it behave? I'm going to paste my suspect from before, and if we command-click into observable, we will see that there's really not much here. There's some implementation details we'll take a look at in a moment, but in terms of publicly accessible APIs, the only real inlet into this package is this with observation tracking function, and it has a fairly complex looking function signature, but let's try to call it back in this file. So if we type with observation tracking, we'll see that it's a function with two arguments. Apply closure that returns some type T. Whatever apply returns will be returned by the overall method here. And then there's this onChange closure that's passed in as well. What does this mean? How are these used? Let's explore that right now. In order for this to work, we'll need an observable value. So let's make a suspect. I'm going to make a glib butler of a reasonable level of suspiciousness. And the way this works is as follows. You first have some code in here. I'm going to make a print here that says I am observing suspect.name. And then you add an onChange callback. You put a closure in here, so I'm going to say name changed. And if I run this as is, all we see is I'm observing glib butler, so nothing interesting happened. Name changed was never printed out. If we access the name again down here, printing suspect.name, name changed doesn't get printed out. But if we were to instead change the suspect's name to perhaps Timorous Maitre D and run this again, we will see that name changed was indeed called. So far we can see that this callback's going to get called if we modify a value that was referred to in this apply closure. If I don't have this property referred to in here, it won't print anything. If I refer to just the suspect, it won't print anything. If I refer to just the suspiciousness, it won't print anything. Only if I refer to this name property will it then print name changed upon this property's subsequent mutation. Another interesting thing to note, if I add some labels here, and then if I modify the name again, Gregor Samsa, we'll see that this closure, this onChange callback, was only executed after the initial change, so it was never executed again. This is a one-shot closure. It gets discarded after being called the first time. Even if I also list the suspect's suspiciousness, and let's say increase it. So if I run this changed callback is still only executed once. It will execute whenever the first item is changed. There's some other interesting details. We can keep adding on the complexity because this is a rather nuanced method. If we have a second suspect, let's bring back Jimmy the Shrimp, and let's refer to Jimmy the Shrimp's properties in here. And I'm going to set Jimmy the Shrimp's suspiciousness to a very high level as well. We'll see that behaves similarly. This onChange callback is only executed a single time. We could even see what happens if we modify these in other threads. So let's look at this example. I create a new thread where I update suspect 2's suspiciousness, sleep for a second, update in another thread the original suspect suspiciousness, and when I run this, we see only one callback. Now there is, however, a bit of a race condition. If I don't have this sleep in here and break off both threads at essentially the same time, we will see that the callback actually does get called twice. Sometimes I ran it again and it didn't get called, so there's a bit of non-determinism here. It depends on how lucky you get. Here it was called twice. So there is something suspicious going on. There's all this behavior. Clearly, it's not a hard guarantee that the callback will only be evaluated once, especially when concurrency is taken into effect, but it certainly attempts to limit it to be at most once. If it is synchronous code, it certainly will be at most once. But if you happen to modify the value at the same time, or nearly the exact same time on multiple threads, there is a chance that it will execute that callback multiple times. So yeah, a lot of details here, but at a high level, you reference some properties in here, and the callback will get executed probably at most once when one of those properties are mutated. There are other things we could explore. Firstly, I could call this a second time, and what would we expect to see happen now? I'll just change suspect. Let me get rid of the second one here to simplify things. So now we're observing twice. So 1, 2, 2, and 1. If I run this, bring this up just a tiny bit, we'll see that there are 2 callbacks. May run this again, 2 callbacks. And it looks like the order is not really deterministic either, depending on how I run it. Sometimes the first callback will get executed first, sometimes the second one will. But once again, if I were to update this a second time, we'll see that each callback was only executed once, which is a semi-guarantee modulo concurrency. So whenever you call with observation tracked, it will associate this callback with the properties on that particular object, right? If I modify suspect 2, nothing will get printed because we're never referring to suspect 2's name in here. So it's both the object and the key path that matter. And then if you ever modify that object's key path, later on, these associated callbacks will be executed. One final case to explore here is if we nest this, what will happen here? In fact, I'm going to remove this first print line. So we're going to track within a track. What will we see? Oh, well, I would have to modify suspect instead of suspect 2. Let's run this one more time. And we see that both callbacks are executed and they're only executed once. So this nested execution does indeed count for this outer execution. Now, what if we, in the outer track, only track the name, and in the inner tracking, track suspiciousness, and then we'll see what happens. If we modify suspiciousness, I would expect to see both callbacks, and that's indeed true. And if I just update the name to Jim Shrimp, as his mother calls him, we'll see that only the initial callback was executed. And then if I later update suspiciousness, we'll see then, at that point, it will trigger 2, but not 1 again. 1 was changed because of this, 2 was executed because of the change to suspiciousness. Whereas I flip it, both changes will occur before C, so suspiciousness triggers everything. So working your way out, suspiciousness was called inside of this apply, so we've registered this callback with suspiciousness and this callback with suspiciousness. So if we modify suspiciousness, both callbacks are triggered and discarded. If we flip the order here and modify name first, only this callback is associated with name. This one is not. So when we modify name, this callback is triggered and discarded. And then when we later on modify suspiciousness, this callback is still available to get triggered. So if I just modify name, only the top one is discarded. If I just modify suspiciousness, both get triggered. And if I modify first name and then suspiciousness, both are triggered by the different times in different transactions. Name triggering the outer onChange, suspiciousness triggering the inner one. Okay, and obviously we can combine this and have multiple objects and test this under concurrency and all that stuff, but I think we're starting to get the idea here, which if you forget a little bit about these more nuanced details, when you call with observation tracking, properties that are accessed in here will somehow seemingly magically have this callback registered with them such that later on in the program, potentially on another thread, years from now, as long as the program hasn't quit, when those are modified, it will call that callback. So that's the behavior. The next step is to actually implement this ourselves to understand what's happening. And we're going to do this in a couple of stages because it's actually a little complicated. At its core, it's a simple idea, but dealing with all of those edge cases, in particular, the ability to discard the observations no matter which property was called. So if we call name here, we want to make sure to discard this closure and never call it again. Similarly, this even works across objects. So modifying the initial suspect's name here will actually discard the callback even on suspect 2's suspiciousness, so that this modification to suspiciousness does not trigger this callback, even though it would have if we didn't previously modify the suspect's name. So to deal with all of that complexity, it gets a little weird. You've got to track a moderate amount in your head and deal with some potentially novel concepts in Swift using low-level concurrency safe data structures and sort of magic global values. We'll look at that all in a second, but we're going to build up starting with a very simple implementation that will at least work for the basic case, and then we can slowly ramp up complexity after we get that through our heads. Because there's enough even just with registering a callback with a single property and getting that to trigger on this property, but not trigger on this property. That's already going to involve some fun stuff, so let's get started. Okay, so the first thing is to just think, how is this even happening? This is somewhat magical. If I look at this class here, okay, it's a little suspicious as it's called suspect, but beyond that, it looks like a normal class. Name and suspiciousness are just normal vars here. How can simply executing this callback track anything? There's no ability to introspect a closure argument. Right? Apply is just this function, this closure here. That's that first argument. How are we going to know what's called here? There is one piece of magic involved, and that is this @observable attribute, this attached macro. And I recorded a video on this a couple weeks ago. Take a look at it if you'd like to learn more about how macros work. But basically, this gets to rewrite your code somewhat. It gets to add things to your code in particular and rework some things. And so things are not exactly as they appear. Luckily, in Xcode, we can peek behind the curtain. There is this quick action expand macro if we put our cursor inside of observable, and we'll be able to look at what the macro actually turns our code into. So that's all this code with a slightly brighter background. This is what is generated at compile time. So it added a whole bunch of stuff. One thing to note is that it added actually a nested macro, which is something macros can do. Observation tracked onto our two variables here. So that's very important. I'm going to expand those as well. And we'll see what happened here is that it turned what seemed to be just normal variables into computed properties with getters and setters, and it relegated the actual storage of these values, this name string and the suspiciousness int, to this underscore prefixed variable below. So our initial name and suspiciousness got pushed to the bottom and made private. So this is what's doing the actual storage. And these computed properties allow us to add a little bit of extra secret sauce. Whenever we access our name, not only are we returning the name, but before we return the name, we're calling this access method, passing along a key path to this very property. And similarly, whenever we modify name, we're calling with mutation, passing along a key path to name, and also a closure that actually will do the assignment. So then the next thing to look at is what are access and what are with mutation. I'll scroll down just a little bit, and we'll see that those are actually defined here as well. And so these two functions essentially just delegate once more to this observation registrar type that's been defined for us and hidden away under a underscore and a $sign to make it extra secret. And we essentially delegate to that, calling its access method and its with mutation method, passing along each of the arguments, the key path, and then we also pass along ourselves, the suspect in this case, for some purpose. Who knows? And that's about as far as expanding the macro will take us. Luckily, unlike a lot of code that Apple ships, this is not secret like SwiftUI. This is not proprietary. This is actually in their open source repo. So you can look at the implementation of observation registrar and access and all of that. And that's what I've done already to understand what's happening. But it took a while to get it into my head. And so I hope we can work through this in a simpler, more incremental way and build this ourselves. So the first thing I want to do is just actually inline some of this stuff. One nice thing about Swift macros is that the code they expand into has to be callable as though you just written it inline. So they can't refer to any secret properties, anything accessible here has to be accessible as though we just written it ourselves. So observation registrar can't be some internal private struct. It has to be callable exactly like this. So what I'm going to do is steal this code and steal this code. And then I'm going to close these, hide the expanded macros. Then I'm going to start pasting that code. So we'll get the same exact stuff. So there's name, and then suspiciousness will be the same, except suspiciousness is an int, and I'll just have it refer to the underscore suspiciousness field, and it will pass along suspiciousness key path, and it'll modify suspiciousness. Okay, so here is our new class, and then I have to do one last thing actually. Observable also added a conformance to this observable protocol, which is also exported in observation, and it has no real functionality associated with it. It is just used as a marker protocol so that other methods, such as with mutation, can ensure that the object passed in was marked as observable. You can really extend anything to be observable, but perhaps this will be used in the future, or it's just a nice little extra piece of type safety to make sure you don't accidentally pass in the wrong thing here. Okay, so reviewing what we have once more, we initialize our suspect with a name and a suspiciousness, and once again at this point, this is going to actually access our setters on these computed properties and trigger with mutation, which I think there's a reason why the macro doesn't change the initializer. I'm not sure if it can override the initializer. It can add code, it can turn things into computed properties. I'm not sure if it can actually just delete the implementation of initialize. So I'm going to change this myself just so we don't have extra noise when we start printing things out. It shouldn't matter because you can't really start observing or tracking a suspect before you've initialized it, so I don't think that will really matter. Okay, so then we have these computed properties. We have these two helper functions we'll look at in a moment. I'm going to remove these attributes, which would just tell the observation macro not to track certain properties. So it's added that to these properties that it didn't want to track. And then there we go. Let me simplify this a little bit and rebuild. Okay, first thing I can do is just run this again. And we'll see that if I scroll down here, it still prints out this callback when I change a value. So we've just expanded the macro. It's still doing the same exact thing. That's great. But now we have a little more of a clue as to potentially how this could be implemented. So one piece of the puzzle is that when we call suspect.name, what we're actually doing is calling suspect.access name. And then we're returning, of course, underscore name, but that's not really relevant to us. We're secretly behind the scenes also calling access with a key path representing that property. And so that's clearly going to be where one piece of the puzzle lies. How access works, what happens when we call access, and the true implementation is nested within this observation registrar. And so I'm going to scroll down here again, but that doesn't really make it fully obvious how this works, because what this is not taking in is this onChange closure in any way. It's simply passing along the key path. How could this with observation tracking possibly associate this callback, this closure, with that key path if this is all it's doing? Clearly there's something else here. And to think about that, let's just actually bring in the signature for with observation tracking and start making our own version of it. I'm going to break this onto separate lines, and I'm going to reformat, and let me just add the beginnings of a body. We'll see that we need to return some type T, which we are going to get by calling apply. So let me at least get this boilerplate in here, and then there we go. Okay, so we're certainly going to call apply, which we know is going to be able to call access on any observable properties that are accessed in that apply. So that's great. But how are we going to associate this onChange with those? How can we possibly pass along an argument to a function that doesn't take parameters? On the other side of things, when we modify suspect.name, and we know that behind the scenes suspect with mutation is called with name, well, we can imagine that if the registrar has already been given this callback, somewhere inside of its registrar we're storing that. We can imagine it has some list of callbacks somewhere, and we can access that with this name key path. Then we can call it somewhere inside of registrar if we have previously stored onChange. It's not so mysterious how we might call that callback. If it's in some dictionary, we don't exactly know what that's going to look like, but this is less of a leap than how are we going to get this onChange callback into this registrar of an object. It doesn't even know what objects are called in apply. This is completely opaque. And it's not too tough of a riddle if you just relax your sense of, decency and safety. You don't try to overcomplicate things. As a clue, let's imagine we had the following API, this print name function, and we wanted this to print a name, print something that was previously passed into my name is. So the way this should work is at one step, we call my name is, and then later on, print name should print this name to the console. How could we possibly get these two functions to work like this with this API? If I did a different name here, it should print a different name. Putting it like this, you might not think it's the most beautiful thing in the world, but you might have some external global name variable, and then simply this would set the global name, and this could then access the global name. And if we run this code, we'll see Sally getting printed. And if I were to instead change this to Kit, we should see Kit getting printed. So this is not particularly mind-bending. It would only be tricky if we're preventing ourselves from considering the use of mutable global state, or global mutable state, or however you prefer to order those adjectives. So with that interlude out of the way, priming our minds, how could we possibly do something here in step 1 that would allow any accesses called within the supply to do something that would potentially allow us to associate this closure here with those key paths? And maybe you're a super genius and have seen 10 steps ahead, but we're going to start with a very simple way of doing this. It's not going to solve all of the complicated edge cases we looked at before, but it's going to get us to pass this first test of being able to associate a callback with a single key path and discard it after we finally modified that key path. So we're going to start simple, and this is how it's going to work. We're going to introduce some global state. I'm going to make onChange closure here, and this is going to be of type sendable, nullery function that returns void here, and we'll make this optional as well. So what we could do is, at the beginning of with observation tracking, before we call apply, we can set this onChange closure equal to our onChange closure. This is actually a little extra complicated because if you look here, onChange is a closure that's been wrapped in another closure, and that is for the purpose of lazy evaluation. So we would have to call this function to get our closure. And the reason why that might be is, well, maybe nothing in here actually is observable, and therefore we never need to track this closure on anything. Therefore, if this closure somehow did something very expensive inside of it to create it, then there's really no point in even creating this closure. So we can make the creation of this closure lazy by wrapping it in another closure. And that's good for the actual implementation, especially because we might imagine that in the real SwiftUI usage of this, a view's body might be called in here, and it doesn't know ahead of time, is there something in here that's definitely going to be tracked or not? And we wouldn't want to waste precious time constructing closures. So it's a bit of a performance optimization. So we can simplify this just by deleting that bit and saying this is going to be an escaping closure, so we can store it elsewhere and then we don't call it here. So we're going to take our closure argument and shove it off into this globally accessible variable here with the intention for access, which is built to be used with observation tracking. These are two halves of the same algorithm, two pieces of the handshake. We're going to stash the closure in here such that later on any accesses called inside of apply can grab this closure and stash them within the observation registrar such that later on we can call them. It's actually rather simple at this point. If that all sounds a little weird, let's actually now implement access. So I'm going to scroll up just a bit. We'll see that observation registrar, we're actually using the real observation registrar, which has these methods. So I'm going to steal this implementation, this interface at least, and come back here and I'm going to paste it right above with observation tracking. I'm going to get rid of some things. I'm going to get rid of all the public keywords because space is limited here. I'm going to format, and then I'm going to delete these will set and did set methods, which are actually never called in our implementation. Technically they're called with mutation, but we can just get rid of that extra code. We won't do anything inside of access for now. And then inside of with mutation, to get this to compile, we'll need to return a T, and that is done by calling mutation. So we'll just return mutation, and that can throw. So I will say try, and now things are building. And so now the code should be using our custom observation registrar to test that out. I'm going to just throw in some prints here. So I'm going to say print access at key path, and same with mutation. I'm going to say with mutation at key path. And then I'm going to run our code again, and I'm going to scroll down, and we see that with mutation was called because all we've done is mutate the suspect's name. And I commented out this print line, so let me uncomment that and run this again, and we'll see that, yes, at the very beginning, before A, we've called access suspect.name, and that was printed to the screen before I'm observing glib butler was printed, and that's because obviously we access name to create that string. And then we printed A, and then we printed with mutation, and then we printed C, and we've never printed our onChange closure because, well, now we've replaced the actual working implementation with our print line method. So let's scroll back up here and actually get this to work. So we know that we've called access here inside of this apply. So keep in mind, we've set the global onChange closure. So if I run this one more time, we'll see that, yes, we're doing that first before access is called, which means that we have access to it in here. I'm going to hide the console for a moment. So then in here, we can start by being extremely hacky and just have a callback which can be an optional one of these values as a var. And for now, we'll just take whatever that global onChange closure is anytime there is a callback, and set callback to onChange closure. So not even worry ourselves with key path at the moment. And then later on, with mutation, we can simply call our callback if it exists. Now that's the hackiest thing in the world, but we'll see what this does. Now, there is a problem, which is that self is immutable because this is a struct. We copied this from the actual implementation, but it turns out the actual implementation is doing a few things to allow such a thing to compile. It's not storing mutable state directly on this struct. It is using an intermediate box type that mediates access using a lock, such that a callback state, any other state we throw in here, is going to be safe to access and modify concurrently across threads. But we're not going to worry about that right now. Perhaps I'll make a follow-up video if people are interested looking into those techniques. I think they're super interesting. But for now, we're going to make this very simple for ourselves and just turn this into a class, which is not actually sendable at this point for a few reasons. So we're going to say, don't worry about that. We don't care. Okay, so with this in place, I'm going to run our code again, and we'll see that our callback was called. This is not particularly mysterious. If we consider what is happening here, let me scroll down to our call to with observation tracking. So here we have everything relevant on the screen. We're calling with observation tracking. Once we do that, we take the closure and store it globally. Then we call apply, which is going to reach into that globally stashed closure and store it locally inside of the suspect's registrar, such that later on, when we mutate our suspect down here, that's calling with mutation, which is going to look into now the registrar on itself and call the callback there. Hooray. But obviously, this is not good at all, because the way we've written it is if I change suspiciousness, it will still call the callback, because we're just storing any old closure. It's really bad, obviously, but we can at least see the general shape of this algorithm. And now we just need to clean it up. Oops, I hit undo one too many times. Okay, so how can we make this a little safer? Well, we don't want this callback to be called just by any mutation. We want the mutation to be associated with the key path. So perhaps I can make this little registry value that can associate with any key path a callback, this type here. And then instead of storing the callback like this, we can have one callback per key path. And now we just have to change this a little bit to take our registry, and at our key path, we can store the onChange closure. And perhaps we should say if closure is equal to onChange closure. So if that is defined, we'll store it. Great. And I also need to give this a default empty dictionary value. And then lastly, use the let keyword there. Oh, and then of course, use it. So if that global closure is defined, we'll stash it at the key path that was accessed, such that later on, instead of calling any old callback, we can if let closure equals registry at key path, or we can even use remove value for key, which will simultaneously access it and remove it. And then, if it exists, we can call the closure. And so now if I run our program, we'll see it still prints. We scroll down to the bottom. So we're observing name. If I modify name, it prints. If I modify name and then subsequently modify suspiciousness, we'll see that with mutation suspiciousness is called, but it does not trigger the callback again. And in fact, if I never modify the name, but only suspiciousness, we'll see that it does not trigger the callback. Name has to be modified for it to find the callback associated with that key path and execute it. And if I modify name multiple times, we'll see it's only ever executed the first time, and subsequent mutations have no effect because we've removed it at that point. So this is not fully powered. Obviously, we'll look at some of its weaknesses, but this is the general shape of what we need to do. And if you can understand this, this is a good sort of base camp to rest at before ascending to the more complicated pieces, parts of the algorithm. So the tricks are the little magic involved in the actual implementation and in this demo, this pedagogical replica, are the same. Actually, the first trick is the trick of, well, macros, such that what seem to be simple accesses to stored values actually get rewritten by the macro into really these proxied methods that decorate these accesses, tracking the key paths that have been accessed and tracking mutations with their key paths as well for each property. And we actually store those initial values in these underscore prefix things. It also creates this observation registrar, which stores inside of it closures associated with key paths for them to be called later. And the other magic trick is that when we first looked at the signature of with observation tracking and thought about how can this possibly make sense, the way that this closure is associated with key paths accessed in this apply is, well, it has to use some form of global mutable state. Now, In the actual implementation, this is truly a global mutable var. It is what is known as a thread local. So it uses thread local storage, which is almost the same thing. It's a global mutable variable, except there's one copy per thread. So global per operating system thread, mutable variable. And this will solve the potentially very weird and awful issues you would have otherwise, where if you called with observation tracking on multiple threads, you might get the wrong closure associated with the wrong properties, and things would just get very strange. But as long as every thread has its own global state, the supply method is not marked as asynchronous. And one thing we didn't try was actually forking a task or another thread inside of apply, but that wouldn't be tracked. Anything forked wouldn't be tracked. This is meant to be synchronous, the supply method. And so we're basically guaranteed that this is going to run contiguously. It's not going to yield to some other part of our program. Maybe the operating system will deschedule it and run your mail application for a minute, but when it's running our Swift program, it's not going to be clobbered. So it's going to run on the same thread, and we're certain that the thread local state, whatever that is, will not be clobbered by some concurrently running observation tracking invocation. So that's the trick. It is global mutable state, macros, and yeah, that's what allows us to pass off some state into something else near. We're throwing a ball into the air, expecting someone to catch it elsewhere in the code. So it's a little hard to read and think about and reason about, but if we track the order of operations and we build our API so that there are these certain invariants, and we're very careful, aka if the actual authors of these APIs are very careful, which I'm sure they are, and test this code thoroughly, then they can actually get away with these pretty cool, seemingly magical properties at what at first seems completely flabbergasting. How are they tracking properties accessed in some completely opaque closure and associating that with a callback? It actually is fairly mundane. It's what you would do in a very simple example. It's what you might have trained your mind to not even consider as a possibility because of the dangers inherent with global mutable state and all that.
Hi, I am a robot voice, Hamburger Helicopter. Kit has left for part 2, which means you have reached the end of part 1. Search around your screen for a button taking you to part 2, wherein we'll make this closer to the real thing, replicating the semantics of the true, standard library implementation. See you there, Cheeseburger Pterodactyl.